Yes. Hi, I'm Devina Mohan. I'm a PhD student at the University of Manchester. And today I'll be talking about exploring galaxy morphology as a probe of dark matter and baryonic physics using machine learning. And this is joint work with Paco and Sebastian. So, to begin with, we know that the matter that we can see in the universe only makes up for about 5% of the total energy budget, and the other 95% still remains elusive, and we don't really know a lot. We don't really know a lot about dark matter and dark energy. And the lambda CDM model has been widely accepted for to explain the structure formation and evolution of structure within the universe. But there are still some small scale challenges to this lambda CDM model. For instance, the missing satellites problem, which now has become the problem of too many satellites, or the core cusp problem, which I've shown here, which the lambda CDM model predicts that the radial density distribution of dark matter around galaxies increases towards the core, but observation suggests that this distribution flattens out, which is the dashed line that we see on this plot. And then there's also the too big to fail problem. So, to study these small scale challenges, we need a controlled environment within which we can vary the effect of the baryonic effects, different dark matter models, and also the different cosmological parameters. And to do that, we use the dream simulations. So this is dark matter with AI and simulations, and it is a huge suite of thousands of n-body and cosmological hydrodynamical simulations, which contain simulations done with different dark matter models at different scales and different particle masses. So, for instance, we have cosmological boxes, some Milky Way like zoom-ins, and also dwarf galaxies. So, from this suite of simulations, we picked the warm dark matter mass simulations. And within that, we look at the Milky Way like zoom-ins. So, these are around 1024 Milky Way zoom-ins. And we also look at the central galaxy from around 300 different views. So, our uh, this makes up the training set for our machine learning models. And this is what the images from this zoom in suite look like. So we can see that these images have very distinct morphologies, and these have been generated keeping all of the cosmological parameters fixed, but then some baryonic parameters which uh, some baryonic parameters like the supernova feedback and the AGN feedback are varied along with the warm dark matter particle mass. So the main question that we wanted to answer with this project was that is there enough signal in these simulated galaxies to predict the warm dark matter mass from the images of these gas density projections using machine learning models? And since we are working with images, we used something called Zubot. So Zubot is a state-of-the-art deep learning classifier, and this has been designed specifically to solve galaxy morphology related problems. So this work was done by Mike Wormsley, and this is the largest. So this model has been trained on the largest collection of labeled images. So there were around 800,000 galaxy images, and then these models were trained using volunteer votes from the Galaxy Zoo Citizen Science Project, which amassed more than 100 million volunteer votes. And the data set contains real galaxies from different surveys, and also the ZooBot models are a whole suite of um, machine learning models, and most of these are CNN-like models, or some of these are also transformers. And based on the complexity of the task, we can choose a specific architecture to solve the task at hand. And one of the advantages of using a pre-trained model such as this is that we need very few training samples of new data in order to answer any scientific question. So among all of these different architectures, we chose the ResNet 18 model, which has around 11 billion parameters. And then we removed the final classification head of this model and replaced it with a regression head, and replaced it with a regression head to predict the parameters of our simulation. So just to show a sanity check, or just to show that there are no zero-shot capabilities with a pre-trained model for our particular prediction task. These are the true and predicted warm dark matter mass, AGN, and the two supernova feedback parameters. And these plots show that if we just pass all of our simulations through the model cannot predict anything, which is a good thing, which is a good sanity check to do. Um, and we find that these models cannot infer any warm dark matter mass just from the gas density projection of the Milky Way like simulations. So the main answer to the question we set out to answer is a null result. But on the way, we found that these machine learning models are able to learn something about the baryonic physics, or the AGN and supernova feedback parameters. So these plots show different um, the output of the model for fine-tuning different heads within the model. So the top row shows what happens if we only tune the final regression layer of the model, and the subsequent rows show the results for what happens if we fine-tune several layers deeper into the network. And we can see that the predictions of the models improve slightly. And finally, we also looked at the effect of the number of views on predicting all of these different parameters. And here I'm showing the mean absolute error and the mean squared error for all of the four simulation parameters that we considered. And again, we can see that um, the strongest signal that the models are sensitive to is for the supernova SN1 and SN2 feedback parameters. So through through this study, we found that galaxy morphology encodes baryonic feedback signatures to different degrees in these simulations, and these are more sensitive specifically to the supernova feedback parameters. And then we also found that fine-tuning only the linear head of the pre-trained ResNet 18 model from ZooBot is able to learn as much signal for these different SN1, SN2, and AGN parameters as the same model trained from scratch. So this shows the potential benefits of using pre-trained models. And it also takes fewer epochs to reach lower validation loss if more of these logs are fine-tuned. And finally, some potential explanations for why we couldn't detect any warm dark matter mass signal. It could be that the signal on the gas density is very weak and the machine learning models are not sensitive enough to capture that. And it could also be the case that these are overshadowed by different baryonic effects. And another potential explanation could be that there is not, we don't have enough data to train large machine learning models with these simulations, because even though we have around 1,000 simulations and 300 different views of these simulations, um, perhaps all of these different views are uh, acting more as a regularizer during training instead of acting as unique data points. So the model is actually only learning from maybe a few thousand examples instead of a few 100,000. Yeah, and I will leave the conclusions up and also thank everyone at the CCA and also a shout out to all of the CCA and CCQ pre-docs from my cohort.
Thanks a lot. All right. Any questions? And a reminder to use your seat mics. And also, please introduce yourself so she knows who she's talking to. I actually had a question. Could you explain this concept? You mentioned regularization in the last slide for those who are not versed in the jargon of this type of modeling.
Yeah, so because all of these machine learning models are heavily over parameterized, if we just train our model on a small data set, what happens is that these models overfit very quickly. But there are several ways we can prevent that overfitting. And in the general machine learning literature, the way things are done in machine learning, people will sometimes just augment their data. So this could be through standard rotations and reflections. And this introduces a kind of regularization which prevents the model from overfitting. So the hypothesis here is that these different views of the galaxy seen from different angles um, is doing more of that regularization effect instead of providing distinct, unique training data points.
Thanks. Any other questions for Devina? If not, oh, Tobin?
Hey, Davina, I was curious on your scatter point plots where you have one on the x-axis and then, yeah, these ones right here. Um, I guess my question is how you quantify the level of precision required for, claiming that something is a good fit or not, and, how you actually parameterize the scatter around these relations.
Yeah, I think it's very hard to precisely quantify that, especially with machine learning effects, where even if you train with a different initialization, you'll get different results. So the way this is done is that you would ensemble the output of multiple models. But I haven't done that here, so this is just showing the output of a single training run. Um, yeah, it's hard to say how good these really are for, or what level of, or what is a good R to score to measure um, how well the model predicted the different parameters.
All right, let's thank Devina again.